Hello, this is Dr. Marina Wal Sabra Jmail from the Lebanese University. In this chapter, I'm going to talk about the input-output modules and their wiring. So I'm going to begin with the input modules, then the output modules, then talk about digital and analog modules, then talk about the remote modules and introduce HMI. Modules of the PLC come in two different forms. They are either digital or analog. In this image in here, we can see an input module with two different commands, one which is connected to a 12-volt source and the other 24-volt source, and they are both connected to switches. Input modules are inserted into the rack containing several inputs. They are available for analog and digital. We have for 8, 16, 32, we can have other combinations of numbers of inputs. We can have modules with inputs and outputs. We can have modules that are analog and digital at the same time. We have special modules. They are available for inputs like thermocouples, RTDs, high-speed signals like counters and encoders. These special input modules have internal electronic circuitry to adapt the signal to these types of sensors instead of having the sensor and the adaptation circuit that are external. So we buy a PLC knowing that it is going to be connected, let's say, to an RTD. We buy an input module that is special for that. The main tasks of an input module are two. One is that it receives the inputs from the outside world and it adapts it to the internal logic level that the computer has, but it also protects the CPU from the outside world, and this is what we call the opto-isolation. The opto-isolation is an optical isolation, but it means that the electric current that is outside doesn't come into the computer, so there's no electrical connection between the outside world and the connection that we have at the outside of the PLC to connect the sensors and what is inside the PLC. This is to protect the PLC inside. So there is an optical separation. We are going to see in the next slide an image on that. So I have a signal, an electronic signal, which turns a LED on, and there's a light receiver, and the receiver just detects the signal, and since it is digital, it is easily transmitted by light. So this protects the CPU from the external electronic or electrical surges that could happen if I have an error, if I have thunder, if I have any problem that could arise at the actual input. This is the real life, this is the sensors, this is the machine, from the internal memory of the PLC, because this is the expensive part of the PLC. The input wiring is like any other electrical circuit. It has to be a closed circuit. So I can have 2 points. I do have 2 points in the PLC. I have the common point and I have the input, and I put my sensor and usually a source. If I have several inputs that I want to connect together, I can put them in parallel. We can see in here that we have one common point and several input values. In this slide, we can see how to wire the second input parallel to the first one and having the same common. If I have a 3-point sensor, this is the output of the sensor in the middle, and I have a plus and minus for the sensors, so I can connect the output to the input of the PLC, and the plus and minus, I take them from the plus and minus sides of the source, and I connect the negative side of the source to the common, so that I can have a common 0 to avoid having any confusion between the 0 value of the input of the PLC and the 0 value of the source, to avoid having erroneous inputs. So in digital inputs, we can have separate commons. Separate commons are useful if I do not want to connect the common point of different types of sensors together, so I can have them separate. If they are connected from within the PLC, they can make noise one on the other. So many PLCs come with input modules having more than one common point. In case I want to connect the commons together, I can just put a wire between them and I would just connect these commons. So I don't need to, if I don't want the separation of the commons. The use of the bleeder resistance is whenever I have a sensor and I am unable to read the value into the PLC correctly, I have sometimes a zero value that is giving off a current that is too much to be read as a zero, because a zero usually in sensors, it's not like what we have in switches. In switches, it is really an open circuit and I have actual nothing coming into the input of the PLC. Whereas in electronic devices, a zero value is a very small current. So if this very small current is still large for the input of the PLC, we add a resistance in parallel, and this resistance divides the value of the current between the one entering the PLC and the one going off to the ground. And then the input value is going to be read correctly. If this resistor is too small, the current coming into the bleeder resistance is too large, and then the input of the PLC will only read a zero. It will no more read the one. Then we have to put a different value of the resistor. Therefore, the bleeder resistor value has to be correctly calculated, but we do not go in this presentation into more details on this. Output modules. In output modules, we can have them in different types. We have the relay output, which is the most common. We have, for high-speed outputs, we have transistor output for the DC devices, and we have triac outputs for AC devices. So it depends on the type of device I want to control. I can go for either type of output. I have to buy the PLC or the output module with these types. I have a current specification for the output modules. We have individual maximum value and overall maximum value. This means that, let's take an example on a relay output. If I have each relay has a maximum value of 1 ampere, and I have an output module with 8 relays at the output, this does not mean that I can draw 8 amperes out of the 8 relays, because the relays are so close to each other that if one of them heats up, it's going to hit the relays that are next to it. So we would have, let's say, an overall maximum value of 5 amperes for 8 relays, each of 1 ampere maximum output. However, we do not push our PLC output module to the limit. We usually take much less current out of our outputs for security reasons and to protect the PLC. And we can take the value, read the value of the output to an external relay, if we are talking about relay output, and draw the energy from that external relay. This is going to put much less risk on the PLC output module itself. Output modules are normally fused to protect the external loads. So if I have any external extra load, it's going to blow the fuse. Just like in input modules, I can have dual commons in the output modules for outputs that should not be connected as a common as the same common. So I can have dual commons, and if I do not want to have separate commons, I can always connect them together. This is an example on how to wire an output and to put two outputs in parallel together with the same source and the same common. If I talk about analog inputs, I have in here 3 different points for the analog input. You have the differential positive and negative and the common, but in here it's not a common, so it's a ground for each analog input alone. If I have single-ended analog inputs, I connect the output of the sensor to the positive side, the plus side of the input, and I connect the negative side to the ground. And here I have a 3-point single-ended as well input, I have connected the ground to the common ground, the minus side, and to the ground. The positive side is taking energy from the power supply, and the signal output is going to the input of the PLC. If I have a differential input or a differential sensor, on the other hand, the differential sensor gives off two values where I have to read the two values into positive and negative sides of the input, the analog input. If I connect the negative side of the differential sensor to the ground, I would lose the information into the ground. A differential output, for example, in temperature sensors, we have the Seebeck effect and some types of temperature sensors. So the output of this sensor, the information is in the differential value. So I would have to take it into two different points in the input and absolutely not connected to the ground. So this is why the analog inputs of PLCs allow 3 points. One of them is ground and one of them is the negative side of the input value. A protective diode is usually added in the output of the inductive devices. This is to absorb the feedback current that is given from the inductive devices when they are turned off, so that it doesn't go back to the PLC and burn the parts inside. Outputs also have, we can have a bleeder resistor for the same reasons that we discussed in the input modules. So in digital input-output modules, we have different types. We have AC and DC, we have sinking and sourcing. We have in outputs, we have transistor outputs, relay outputs, and triac outputs as well. We have inside the memory of the PLC, for each module, input module, and for each output module, we have what you call an image table. So I have an input image table for the input modules and an output image table for the output modules. The input image table is space in memory where I am going to save the values of the real inputs, and then when I execute the program, I'm going to read from this table into the program, and from the program we are going to take the values into the output image table. And only when the program finishes executing, these values that are here on the output image table, they are going to be loaded to the output module. And once the values are loaded to the output module, the program starts again. It loads the values from the input module to the input image table and then starts executing. So during the execution of the program, there is a separation between the actual physical input module, output module, and the memory corresponding to them. That we call the input image table and the output image table. Analog input-output modules need analog to digital cards. So inside the PLC reads in digital form. At every analog input and every analog output, I have a transformation between the analog value and the digital. A to D are used for the input cards, and D to A are used in the output cards. So these analog to digital values could be current sensing, could be voltage sensing, so they could read the value of the changing current and transform it into a digital value, or read the value of the voltage changing and transform it into a digital form. Most of the sensors that we use are usually store the value, the variation in voltage, so most of the cards are going to be voltage sensing. Analog input modules could be unipolar or bipolar. Unipolar, this means they read only the positive values. Bipolar, read negative values and positive values. The difference is that if I am going to take a range that I know is never going to be positive and I read it into a bipolar card, I am losing of what we call the resolution of my reading. So I have to make the maximum out of the resolution to get correct information into the control. This is why I have to adapt my cards to the type of actual inputs that I have. Very briefly, a transformation from analog to digital happens in this way. We begin with an analog value, which is a continuous variation, into its different steps. So the higher I have a number of bits to code my actual analog input, the better the resolution. This means the smaller this step is, and the smaller the difference between one value and the other is, and I have more values. Therefore, I can read a signal that is more likely to resemble my original analog value. This and here are 8 steps. So 2 to the power 3 is 8. This means I am coding in 3 bits. This is very low. I would code usually in 16 bits, so this is 2 to the power 16, that's 65,000 and something values. And this is usually good for most of the types of control that we have. So we have here a set of examples of different types of input cards, analog input cards. So in here we have plus or minus 10 volt DC. This is a bipolar. In here I have unipolar. So in here the resolution is half. This is why we keep the nominal resolution the same. In here it's using 1 bit less in the coding. So I can, if I use 16 bits with a unipolar card, I will be able to go to a higher resolution. And if I go with the same resolution in a card which is 0 to 5 DC, it is going to code in 14 bits, so it's only going to require 14 bits to have the same resolution. I can in here have current sensing cards, so I have a plus or minus 20 milliamperes. So in here I have a resolution of 1.22 milliamperes per least significant bit. This is the resolution itself. It is the smallest value that the card can sense or detect. So in 15 different bits I can code this. If I go to half the range, this is from 0 to 20 milliamperes, I need only 14 bits to have the same resolution. And I could have cards that go from 4 to 20 milliamperes. This means it eliminates the 0 because it doesn't need it. If I know that my variation of values is never going to go below 4 milliamperes, I can go to a different card. And here when I say 13.67 bits, this is a mathematical value. You know that you cannot get a number of bits that is not an integer. Analog output modules, we have voltage and current output modules, and the same, without going into their details, we have the same type of resolution in the outputs, so they give off the corresponding values. And here we have some examples of cards that we are stating. When I talk about remote input-output modules, it means that if the sensors are very far from the PLC, we can have a input-output module that is far from the PLC and it is connected with a twisted pair to the PLC. Sometimes the sensors cannot be connected with a wire that is very, very long, so we can take the module and put it close to these sensors. So actually we can also nowadays have remote modules that are connected wirelessly to the PLC. We put a wireless module next to the PLC and we connect the sensors to it. A human-machine interface, or an HMI, is a screen where we can program the screen with buttons and displays, so it can work like inputs and outputs, but it is not connected to the input module nor to the output module. It is connected by a different cable into the PLC. It has a separate software, it is programmed alone, and it can address the memory values and it communicates with the PLC. They usually come with the same company, so if you have a PLC from a certain company, you buy the HMI corresponding to that PLC so that their own drivers communicate together, and you can have much less inputs and outputs on your board, but you replace them with the HMI. HMI, since they are screens, they can offer a better display than ordinary outputs. This is the end of chapter 4. Thank you.